We have so far learnt how thin sections of minerals are prepared for microscopic study. We have tried to understand some basic principles of mineral optics. We have also seen the various components of petrographic microscope. With this background, let us now observe some important optical properties of minerals in thin section. We will make these observations in two different modes. In plane polarized light when the analyzer is out of path, and in crossed position when the analyzer is inserted.
The optical properties observed in plane light are color, pleochroism, and relief. A large number of minerals are colorless in thin section. These includes common minerals like quartz and feldspars. There are others that show distinct colors. For example, edgerine shows yellow color, hornblende shows green color, and so on. Color is a diagnostic property of these minerals. There is a difference between colored isotropic and colored anisotropic minerals in terms of absorption characteristics. In isotropic minerals, color does not change on rotating the stage, but in anisotropic minerals, either the shade or the color itself is liable to change when the stage is rotated. This property is called pleochroism. Pleochroism is the result of changing the orientation of mineral with reference to polarizer vibration direction, because of which refractive index and absorption characteristics of the mineral changes. Pleochroism is distinctly observed in minerals like biotite, tourmaline, etc. Pleochroic colors are characteristic features of these minerals. In thin section, we normally come across several grains of either the same mineral or different minerals. Some minerals appear to have more distinct grain boundary than others. The distinction of grain boundary is measured as relief of a mineral. Relief is proportional to contrast in refractive index between a particular mineral grain and those surrounding it. When there is a greater contrast in refractive index, the grain boundary is distinct and the mineral is said to have a high relief. On the other extreme, when there is little or no contrast in refractive index of adjacent grains, the boundary is faintly visible and the relief is low. Quartz and feldspars have low relief compared to mica, garnet, amphibole, and pyroxenes.
Besides these optical properties, two important physical properties, namely crystal form and cleavage, are also observed in plane polarized light. We will now observe these behaviors under the microscope.
Some mineral grains are totally bound by crystal faces as indicated by their regular geometry. Such forms are designated as euhedral. Minerals like apatite and calcite may be found in euhedral form. It is more common to see mineral grains partly bound by crystal faces. Such forms are designated as subhedral. Feldspars, micas, and amphiboles are generally subhedrals. Sometimes mineral grains totally lack in crystal faces. Such forms are called enhedral. Quartz commonly occur as enhedral grains. Further, on the basis of shape, mineral grains can be distinguished as equant and elongated forms. Garnet is invariably equant. Acicular or needle-like minerals, for example, sillimanite, actinolite, etc., are recognized by the distinct elongation along one axis. In thin section, cleavage of a mineral is seen in the form of parallel set of dark lines confined to a mineral grain. Micas, like biotite and muscovite, are characterized by one set of perfect cleavages. Amphibold group of minerals show two sets of cleavages intersecting at about 120 degree.
We will now observe the minerals after inserting the analyzer, that is the upper polarizer, in the optical path.
We find several changes in the appearance of minerals. Isotropic and anisotropic minerals can be readily distinguished in crossed position. Since isotropic minerals do not modify the vibration direction of incident light, the light transmitted by these minerals is totally absorbed by the analyzer. Hence, isotropic minerals remain dark in all positions during rotation of the stage. Anisotropic minerals, however, modify the vibration direction of incident light by double refraction. This tendency to modify the character of incident light varies with the rotation of microscope stage, causing change in the appearance of the mineral. During rotation of the stage, the mineral grain assumes darkness at every 90 degree intervals. These are called extinction positions. In other positions, the mineral shows a distinct color. The intensity of this color is maximum at 45 degree from extinction position. This color is the result of interference of light rays having definite phase difference, where the phase difference is set by and is proportional to the birefringence of the mineral. It is therefore called interference color. We can assign the order of interference color of a mineral by comparison with a standard chart of interference colors. First order colors, namely gray and yellow, are dull. Relatively second and third order colors are quite distinct and bright. In higher orders, the colors become less distinct. Larger the birefringence of a mineral, higher the order of interference color. Quartz having a birefringence of 0.009 shows pale yellow interference color of first order. All feldspars have smaller birefringence and hence show first order gray interference color. Muscovite, which is colorless in plain polarized light, shows brighter interference colors of third order in crossed position. Calcite, having a large birefringence of 0.172, shows fourth order colors. When a grain of anisotropic mineral shows cleavage lines, crystal faces, or elongation along one axis, the angular relation between any of these crystallographic orientations and the extinction position can be observed. By this relation, it is possible to distinguish uniaxial and biaxial minerals. In uniaxial minerals, we will find that at extinction position, the elongation direction or cleavage lines of the minerals are parallel to one of the two hairlines of eyepiece. You will recollect that the orientation of these hairlines correspond to the vibration direction of polarizer and analyzer. In this case, extinction angle is 0 degree. It is called straight extinction. Tourmaline, being a tetragonal mineral, shows straight extinction. Biaxial minerals belonging to orthorhombic system will also show straight extinction. In other biaxial minerals, it is seen that at extinction position, cleavage lines or other such reference lines are oblique to the hairlines. It is called inclined extinction. The smaller angle between the reference line of mineral and the hairline is measured as extinction angle. Extinction angles of 15 to 20 degrees are common to amphiboles, while angles greater than 20 degrees are characteristic of pyroxenes. Twinning is another feature that is observed in crossed position. In a normal crystal, the entire grain of a mineral will have a common crystallographic orientation and therefore arrive at extinction position at the same time. Twinning in minerals represent a deviation from normal crystal habit. In twinned crystals, different segments of the same grain will be having different crystallographic orientation. Therefore, when some portion is in extinction position, other portion shows interference color. There may be two or more twin components within a mineral grain. Feldspars show different forms of twinning. Plagioclase feldspars invariably show multiple twinning. Orthoclase shows simple twinning. The world of minerals is indeed colorful under the microscope. When you are able to recognize a mineral, it adds to your delight.